Welcome to Study Loop.
We're given a vector field F and surface S, and we're asked to use the divergence theorem to calculate the surface integral over S of F. So F is the vector field magnitude of R times R, where R is the vector xi plus yj plus zk, and S consists of the hemisphere z equals the square root of 1 minus x squared minus y squared, and the disk x squared plus y squared is less than or equal to 1 in the xy plane. So first of all, let's write out f in its entirety as a function of x, y, and z. So this is going to be, well, we have that r is xi, yj, zk, so this is x times the norm of r, which is the square root of x squared plus y squared plus z squared, I, plus y times the square root of x squared plus y squared plus z squared, j, plus z times the square root of x squared plus y squared plus z squared, k, and therefore the divergence of f, this is going to be taking a partial derivative of the first component with respect to x. We use the product rule, so we have x times 1/2 times x squared plus y squared plus z squared to the negative 1/2 times 2x, and then plus the derivative of x is just 1 times the square root of x squared plus y squared plus z squared. And in fact, we repeat this pattern with y and z taking the role of x, so we add y times 1/2 times x squared plus y squared plus z squared to the negative 1/2 times 2y plus x squared plus y squared plus z squared to the 1/2 plus z times 1/2 times x squared plus y squared plus z squared to the negative 1/2 times 2z plus x squared plus y squared plus z squared to the 1/2, and combining terms and factoring out x squared plus y squared plus z squared to the negative 1/2, we get x squared plus y squared plus z squared to the negative 1/2 times, and this is x squared plus x squared plus y squared plus z squared plus y squared plus x squared plus y squared plus z squared plus z squared plus x squared plus y squared plus z squared. And combining, we get 4 times x squared plus y squared plus z squared over the square root of x squared plus y squared plus z squared, which of course is the same as 4 times the square root of x squared plus y squared plus z squared. By the divergence theorem, the surface integral over S of f is equal to the triple integral over the region E bounded by S of the divergence of f, which is 4 times the square root of x squared plus y squared plus z squared, and the region E, this is a hemisphere which can be described using spherical coordinates easily. So making the switch, this becomes the iterated integral from 0 to pi over 2, integral from 0 to 2 pi, and integral from 0 to the radius of our sphere, which is 1, of our function in terms of spherical coordinates. So we have 4 times rho times the differential rho squared sine phi d rho d theta d phi. And using Fubini's theorem, we can write this as a product of integrals. So we get integral from 0 to pi over 2 sine phi d phi times the integral from 0 to 2 pi d theta times the integral from 0 to 1 of 4 rho cubed d rho. And then taking antiderivatives, we get negative cosine phi from 0 to pi over 2 times theta from 0 to 2 pi times rho to the 4th from 0 to 1. And evaluating, we get negative 1 times, it's actually opposite of negative 1, so it's positive 1 times 2 pi times 1, which is simply 2 pi.